My name is Josh Mutus. I'm the Director of Quantum Materials at Rigetti, and I do a number of things, but one of these is trying to basically figure out what limits performance and adds defects to our to superconducting qubits. And I'm going to start here by saying, and kind of echoing something that was said earlier, but like loss and defects in superconducting qubits is a grand challenge in the field. We know that there's this kind of boogeyman, a two-level system, but we don't actually know what it is. And we have to constantly be trying to find that and increase the lifetimes of our qubits while making them more scalable and better. And like was mentioned earlier, we know that measurement outcomes empirically vary in time. They vary from cooldown to cooldown. They vary from device to device. So we need to be able to cast a really wide net in terms of materials and processing techniques to solve these issues, but handle this ambiguity. So we have to be able to make sure that collaborative research happening at labs across the world have results that translate. And I'm going to touch on a project that we're doing to try to get at this round robin project. And what we're going to do is measure identical devices in different labs, quantify the distributions, and figure out how to make these things translatable from lab to lab. However, this requires that we have many identical things, an identical protocol for this inter-laboratory comparison. So the actual where the rubber meets the road is this SQMS-led round robin measurement project that we're doing. And this slide is a little dated because it actually includes NPL. There's several sites here across the United States, one in Italy at Gran Sasso, and then one now at the NPL laboratories that we were speaking earlier. And the goal here is pretty simple. We want to do a simple superconducting qubit characterization protocol at multiple sites. We want to quantify the impact of the environment, the apparatus, the repeated cooldowns, simply like moving the chip from site to site to see statistically what's going on here. But what this means is that we have to do the same thing in multiple different places. And one of the things that I think is particularly relevant to some of the folks on the panel here is that every lab has, almost every lab has a different set of electronics. And we want to do nominally a simple thing is measure these like headline performance specifications, T1, T2 dephasing, high frequency dephasing. But there's many details that come up in these relatively simple measurements, like the number of points that you're taking, the repetition rate, how quickly you're getting these time series of data, what the cutoff frequency is for your echo experiments, and even many more decisions on how we're calibrating the system. A protocol is going to require consistency, so we get consistent results from lab to lab, and ultimately to say like our fab where we're replicating results and trying to repeat this performance. So one thing that we've actually run into is we write a protocol and then we run into this kind of conundrum. What do we do to make it translate from a lab that has like a Q-block set of electronics or a Zurich instrument set of electronics or a Keysight electronics? After we document the protocol, we agree on everything in a set of slides or a Google Doc. What do we do then? So we have three options as far as I can see it. We can script it in each lab's control electronics, which is kind of manual, requires a lot of expertise. It is essentially re-implementing it, and that can introduce bugs. We could find one set of golden set of control electronics and actually like physically ship it around. This is lengthy. It reduces parallel. You can't do parallel operation. You run into customs. It's highly inefficient. The other option is we could just buy the identical set of control electronics for each lab. But the only kind of financial tractable thing, the value-based option here is this like kickboard, this Xilinx-based system on a chipboard, where we can like actually afford to put this in the lab. So what I kind of wanted to prompt here is like, what are options as a community? I've seen a few like open source things mentioned, but that can actually like help us come at this challenge where we need this reproducibility, we need this uniformity so that we can actually make progress in materials. And that's kind of where I'll leave it.